Assalamu alaikum students, I am Wasim Ikram. This is the 13th lecture in a series of 45 lectures on digital logic design. कैसे हैं आप? इंशाल्लाह सब अच्छे होंगे. पिछले लेक्चर में मैंने आपको एक चैलेंज दिया था. You had to program the Quinn-McCluskey method. कितनों ने किया है उसमें, और वो क्या जो हम सर्किट सोच रहे थे odd prime numbers का, to detect an odd prime number between 0 to 31, वो कुछ एक्सप्रेशन आया. बहुत सारों ने कर लिया, नहीं किया. आज इंशाल्लाह देखेंगे उसको. हम जो था सर्किट जो था उसको हम सॉल्व करेंगे थ्रू क्विन-मैक्लस्की मेथड, जो एक्सप्रेशन था, और फिर चेक करेंगे कि जो आपका आंसर है, हमारा जो इधर आंसर आता है वो एक ही है या कुछ मुख्तलिफ है. Today we will inshallah be discussing combinational logic. Now if you remember, in the very first lecture we mentioned that gates do not perform any useful function. You have to combine gates in different forms to form a logic, a function, which does something useful. For example, comparator circuit, or the odd prime number circuit, or the odd parity circuit, they combine gates in different forms, in different manners, and they form a circuit. So basically, combinational logic is a combination of gates. कैसे connect करेंगे वो आज हम देखेंगे. But before we start our discussion on combinational logic, let us revise the topics which we did in the last lecture. And we also need to complete our discussion on the odd prime number checker circuit. Now, in the last lecture, we started our discussion with functions having multiple outputs. Now, कंपेरेटर सर्किट की हमने एग्जांपल ली थी जिसके 4 इनपुट्स थे, 3 आउटपुट्स थे. तो उसको कैसे हमने उसकी एक्सप्रेशंस लिखनी? बेसिकली वी वुड हैव a truth table with 4 variables, 16 possible inputs, 3 different outputs आ रही हैं. So we would have 3 different expressions representing each output. Expressions कैसे आएंगी? We had 3 different Karnaugh maps. Then we talked about the Quinn-McCluskey method. Quinn-McCluskey method, we said, is a better method, or a method which allows us to simplify expressions having large variables, more variables. So 4 variables तक तो Karnaugh map आपका काम करेगा, उसके बाद Karnaugh map काम नहीं करेगा. So variables, expressions having variables 5, 6 and 7, Quinn-McCluskey method would be applied. Quinn-McCluskey method we said is based on a program होगा जिसके थ्रू आप solve करेंगे. It is a 2-step method. First step में क्या करेंगे? Basically you find the prime implicants. Prime implicants कैसे ढूंढते हैं? Basically you compare all the terms and you try to remove single variables one at a time. When you are unable to remove any variables, that means you have completed step 1. Step 2 में क्या करते हैं? Basically, you have that set of prime implicants, the important product terms. From those essential prime implicants, you select the minimal product terms which represent your expression. उनमें से कुछ redundant होंगे जिनकी जरूरत नहीं है. You can just simply discard them. At the end of last lecture, we talked about finding the expression for a odd prime number generator. जो prime number था हमारा odd prime number, जो input number range था from 0 to 31. So 0 to 31 we require 5 variables. 5 variables को solve करना Karnaugh map से मुश्किल है. Quinn-McCluskey method हमने अप्लाई करना है. So पिछली दफा हमने सारे steps discuss किए थे. Let us have a look at the actual information or the data which we require and which we use. The function for odd prime numbers in the range 0 to 31 is defined in canonical sum form as sigma a b c d e, and the min terms 1, 3, 5, 7, 11, 13, 17, 19, 23, 29 and 31. The min terms represent the odd prime numbers. The min terms along with the variables a, b, c, d and e are written in a tabular form. Each min term is represented in terms of its binary value. We refer to this table as table 1. The table of min terms is reorganized in terms of groups of min terms having 0, 1, 2, 3 and 4 ones. Thus min terms 1 has a single one. The min terms 3, 5 and 17 have 2 ones each. the minterms 7, 11, 13 and 19 have 3 ones each. The minterm 23 and 29 have 4 ones, and minterm 31 has 5 ones. This table is referred to as table 2. Minterm 1 is compared with minterms 3, 5 and 17 in the next group. Similarly, each of the 3 minterms 3, 5 and 17 are compared with each of the minterms in the next group having 3 ones, that is minterms 7, 11, 13 and 19. Minterms 7, 11, 13 and 19 are compared with each of the minterms in the next group having 4 ones, that is minterms 23 and 29. Lastly, each of the 2 minterms 23 and 29 are compared with the minterm 31 in the last group having all ones or 5 ones. The results of the comparisons between 2 minterms are represented in a separate table referred to as table 3. The first column lists the minterms that have been compared together to eliminate common variables. So terms 1 and 3 form a single term eliminating variable D, forming the product term A bar, B bar, C bar, E. The comparison terms 1 and 3 are marked as used in table 2. Similarly, terms 1 and 5 form a single term eliminating variable C, forming the product term A bar, B bar, D bar, E. Both these terms are marked as used in table 2. Terms 1 and 17 eliminate variable A. Terms 3 and 7 eliminate variable C. Terms 3 and 11 eliminate variable B, and so on. As a result of comparison, a total of 14 4-variable product terms are formed, eliminating a single variable from each term. All the 14 terms are represented in table 3. The exhaustive search for finding prime implicants has not completed. An unmarked term represents a prime implicant. The results of the comparisons between 2 terms in table 3 are represented in a separate table referred to as table 4. The first column lists the terms that have been compared together to eliminate common variables. So terms 1, 3, 5 and 7 form a single term eliminating variables C and D, forming the product term A bar, B bar, E. The comparison terms 1, 3 and 5, 7 are marked as used in table 3. Similarly, terms 1, 3, 17 and 19 form a single term eliminating variables A and D, forming the product term B bar, C bar, E. Both these terms are marked as used in table 3. Product terms in table 4 are compared to eliminate common variables. No more comparisons of terms and elimination of variables takes place. Thus, the prime implicants have been found. There are 3 prime implicants in table 4 and 5 prime implicants in table 3. The 8 prime implicants are represented by the product terms A bar, C bar, D, E, A bar, C, D bar, E, B, C, D bar, E, A, C, D, E, A, B, C, E, A bar, B bar, E, B bar, C bar, E, and B bar, D, E. In the second step of Quinn-McCluskey's method, the essential and minimal prime implicants are found. The prime implicants found in the first step are listed in the leftmost column of the table. The table is referred to as table 5. All the original minterms are listed in the top row. So the minterms are 1, 3, 5, 7, 11, 13, 17, 19, 23, 29 and 31. In each cell, an X is marked indicating that the prime implicant listed in the left column covers the minterm mentioned in the top row. Thus, the prime implicant A bar, C bar, D covers the minterms 1 and 5. In other words, minterms 1 and 5 all have the product terms A bar, C bar, D. The table 5 can be directly implemented from table 3 and 4. Circles are marked in cells having X, which represent minterms covered by only a single prime implicant. Thus, the minterms 11 and 17 are covered by only the prime implicants A bar, C bar, D, E and B bar, C bar, E respectively. these implicants do not cover all the minterms. The other essential implicants that have minimum number of variables and which cover all the remaining minterms are B, C, D bar E, A, C, D, E, and A bar, B bar, E. Thus, the simplified expression that represents the odd prime number in the range 0 to 31 is represented by the product terms A bar, C bar, D, E, B, C, D bar, E, A, C, D, E, A bar, B bar, E, and B bar, C bar, E. We just looked at the expression derived for the odd prime number checker circuit. I hope the expression which we have derived here is the same as the expression which you derived using your program. Okay, let us start with the combinational logic. Combinational logic, as we said, is basically combining or combination of different gates. एक अकेले में गेट जो है एंड गेट या और गेट या कोई भी गेट हो, it cannot perform any useful function. So they have to be joined together, they have to be combined together to form or to do some useful function. On what basis can we combine these gates? Basically, the expression which represents a function is used to implement the circuit. So we have a Boolean expression which, let's say, represents the add function. We have a Boolean expression which represents the odd prime number checker circuit. We have an expression which represents the comparator circuit, and so on. The last step would be to implement these expressions using combinational logic or different gates combined together. Now, we have studied two forms of expressions, the sum of product form and the product of sum form. So if you are going to be implementing a circuit or a combination logic circuit, it has to be based on these two expressions, either the sum of product form or the product of sum form. Now, considering the sum of product form expression, basically it has product terms which are added together. So how would you implement a circuit, combination logic circuit, which is based on this sum of product form? Basically, it would have a number of AND gates. Each AND gate would be implementing one of the product terms. You would have a single OR gate which would be adding all the product terms together. So the outputs of all the AND gates would be connected to the inputs of the single OR gate. Now, each of the product terms have complemented input or uncomplemented input. So, for example, you have the product term A, B bar, right? So, how would you implement A, B bar? Basically, you have an AND gate. One of the inputs is connected to A, the other input is connected to B complemented. So, B complement, how would you obtain that? By using a NOT gate. So, basically, implementing a sum of product expression using logic gates, you would have a circuit having three levels of gates. The first level of gates would have the OR gate, which basically sums up all the product terms. The second level would be comprising of all the AND gates, which generate the product terms. The third level of gates would comprise of the inverters, the NOT gates, which complement the different variables and provide them as an input to the AND gates. So three levels of gates. Now, considering the product of sum form of expression, in the product of sum form of Boolean expression, you have sum terms which are ANDed together through an AND gate. So again, if you are going to be implementing a product of sum expression, you would again have a combination circuit having three levels of gates. First level would be comprised of the AND gate. The second level would be comprised of the OR gates, which in fact generate sum terms. And the third level would be comprised of the inverters or the NOT gates, which provide complemented inputs to the OR gates. Let us have a look at the general architecture of the sum of product form of expression, the implementation of sum of product expression, and the implementation of product of sum expression. The diagram shows the general architecture of the sum of product implementation. Sum of product expression is implemented by the AND OR combination of gates. The AND gates produce the product terms, output of all the AND gates are connected to a single multiple input OR gate for sum of products. The product terms comprise of literals in their complemented form and uncomplemented form, which are implemented by NOT gates connected to the inputs of the AND gates. The diagram shows the general architecture of the product of sum implementation. Product of sum expression is implemented by the OR AND combination of gates. The OR gates produce the sum terms. Outputs of all the OR gates are connected to a single multiple input AND gate for product of sum terms. The sum terms comprise of literals in their complemented form and uncomplemented form, which are implemented by NOT gates connected to the inputs of the OR gates. We have just looked at two generalized form of combinational circuits. One form is basically the implementation of sum of product expression. The other implementation is basically the implementation of product of sum Boolean expression. Now, let us look at the entire method. Where do you start? How do you design a circuit? How do you implement a circuit? Let's take an example, the example of a 2-bit adder. Now, what does a 2-bit adder do? Basically, it adds two numbers and each number is of 2 bits. The answer would again be of 2 bits, but a carry might be generated. So basically, the function of a 2-bit adder is to add. Okay. How would you represent the function? Basically, you would draw out a truth table where you would have all the possible inputs and the outputs. Now, how many inputs do you need and how many outputs do you need? Basically, you need 4 inputs representing the two 2-bit numbers and 2-bit output. The adder, of course, also generates a carry, so you need another single bit output representing the carry. The adder might also add a previous carry, so it needs another carry input pin. So now you have defined the function of the adder through a truth table. You have defined the number of inputs and the number of outputs. What do you do next? Basically, you have to represent this function in the form of an expression, a Boolean expression. So how many outputs do you have? You have basically 3 outputs, the two sum outputs and the carry output. Now you can directly implement a combinational circuit from the truth table. Now the truth table, remember, has 3 outputs. It would have different combinations of 1s and 0s. Now to implement, let's say, the carry output, you would select the minterms for which the carry output has been set to 1. So what would be the circuit in terms of sum of product forms? You would have AND gates, which would be generating the product terms for different input combinations. The outputs of all those AND gates would be connected to a single OR gate. The output of the OR gate, single OR gate, would represent the carry out function. Similarly, for the two outputs representing the sum, again you would represent or implement a circuit having multiple AND gates and OR gate. Now, if you implement a circuit directly from the function table, it would of course work, but it would use a large number of gates. Now, if you have large number of gates in your circuit, what happens? Basically, it occupies a large area. The circuit size is going to increase. The power requirement is going to increase. The propagation delay is going to increase. So perhaps it would not be able to work at high frequencies. Now, the best option is to first simplify the expression. How do you simplify the expression? You have the function table, which completely represents the adder function. Now, for each output, you have to come up with a Boolean expression. Use a Karnaugh map or the Quinn-McCluskey method or an appropriate method to simplify the expression. The simplified Boolean expression can then be implemented using combination circuits, logic gates. Now, the combination circuit formed after having simplified the Boolean expression would be simpler, smaller, power requirement would be low, and perhaps propagation delay would be low. So we are going to be looking at some examples which describe such circuits. Let us go through this design procedure. we would be designing a circuit. First of all, we would be defining its function, then perhaps we would be defining its expression, and then implementing the combinational circuit. Now, the circuit which we are going to design is an adjacent 1 detector. What is an adjacent 1 detector? Let's suppose you have 4 bits, 1, 0, 1, 1. Now, in 1, 0, 1, 1, you have 2 adjacent ones. So, if your circuit looks at these 4 bits, it should be able to detect the 2 adjacent ones. If you have another number, 1, 0, 1, 0, now you don't have any adjacent ones, so your circuit should not be able to detect that. Now, first of all, we would be defining the function of this adjacent 1 detector circuit. Once we have defined the function, then we can either directly implement a combination circuit from the function table, or we could have a simple expression represented through a Karnoff map and then implement that. We can also implement a combination circuit based on NAND gates. So let us have a look at the different implementations. The adjacent ones detector circuit accepts a 4-bit binary input and generates a 1 output when it detects a combination of 2 adjacent ones. The function diagram shows the 16 possible input combinations and the corresponding outputs. Thus, for the input combinations 0011, 0110, 0111, 1011, 1100, 1101, 1110, and 1111, the output function is a 1. The information provided by the function table can be directly implemented to form the adjacent ones detector circuit. Now, how many AND gates are required? Basically, 8 gates are required to implement the 8 minterms. As you can see from the function table, the output F is set to 1 for 8 different minterms. So, 8 AND gates are required to implement the 8 product terms. How many OR gates are required? Since it's a sum of product implementation, therefore all the product terms have to be summed together. So a single OR gate is required. The OR gate has 8 inputs. Some NOT gates are also required to implement complemented literals in some of the product terms. The sum of product based implementation of the adjacent ones detector circuit is shown, implemented directly from the function table. The implementation uses maximum number of gates. The total gate count is a single 8 input OR gate, 8 4 input AND gates, and 10 NOT gates. Altogether, 19 gates are required to complete the circuit. The increased number of gates increases the cost, the size of the circuit, the power requirement, and the propagation delay, which is of the order of 3 gates. An appropriate way to implement the adjacent ones detector circuit is to simplify the SOP, or the sum of product Boolean expression represented by the function table, and then implement the circuit based on the simplified expression. The function table information is directly mapped to a 4-variable Karnoff map. The ones are grouped together, forming 3 product terms. The 3 product terms are AB, CD, and BC. The simplified circuit is implemented using 3 2-input AND gates and a single 3-input OR gate. The total circuit count is 4 gates. The cost of the circuit reduces, the size of the circuit reduces, the power requirement of the circuit reduces, and the propagation delay has reduced from 3-gate delay to 2-gate delay. The simplified 4-gate circuit can be implemented using only NAND gates without a change in the total number of gates. Bubbles representing NOT gates are placed at the output of the 3 AND gates, converting the 3 AND gates to NAND gates. To balance out the 3 NOT gates added at the outputs of the 3 AND gates, 3 bubbles representing 3 NOT gates are also placed at the 3 inputs of the OR gate. The resulting OR gate symbol with 3 bubbles at the 3 inputs is an alternate symbol for a 3-input NAND gate. The NAND gate based circuit is shown. We have looked at 3 different implementations of the ones adjacent detector circuit. Basically, we started with the standard sum of product expression. If you look at the function table, you see different min terms. اگر وہ سارے min terms آپ لکھ لیں, you would have a standard sum of product expression. اس کو اگر ڈائریکٹلی ہر min term کو implement کر لیں through an AND gate, you would have the complete circuit. Now this particular circuit requires large number of gates, so the circuit size of course increases. دوسری ہم نے implementation دیکھی تھی. If you simplify the expression, basically وہ جو فنکشن ٹیبل میں سارے min terms ہیں وہ آپ میپ کر دیں, کارنف میپ میں اس کو سمپلیفائی کریں, you end up with 3 product terms. اور اگر اس کو آپ امپلیمنٹ کریں, you get a very simple circuit composed of 4 gates. 3 ان میں سے AND gates ہیں اور ایک اور گیٹ ہے. The last implementation which we saw was the NAND based implementation. سارے جو گیٹس ہیں ان کو ہم نے کنورٹ کر دیے ان دی فارم آف NAND گیٹس. سو ان تینوں سرکٹس کا جو آؤٹ پٹ ہے یا فنکشن ہے وہ بالکل آئیڈینٹیکل ہے. Now we have been saying that if you have a function table where you have all the min terms and the max terms, you can form 2 different type of expressions, a product of sum expression and sum of product expression. Now دونوں ایکسپریشنز جو ہیں ایک ہی بات کر رہی ہیں, وہ دونوں کا آؤٹ پٹ جو ہے ایک ہی آئے گا. Now if you implement both these expressions through AND OR gates or AND gates, the output of the circuit would be identical. So let's check that. ابھی ہم نے جو 3 سرکٹ امپلیمنٹ کیے تھے بیسکلی وہ سم آف پروڈکٹ ایکسپریشن پہ بیسڈ تھے. اب ہم جو ہے دوبارہ سے سرکٹ بنائیں گے, دے وڈ بی بیسڈ آن دی پروڈکٹ آف سم ایکسپریشن. سو اسی طرح یو ہیو دی سیم فنکشن ٹیبل, اس میں اب میکس ٹرمز جو ہیں وہ آپ نے ساری لکھ لینی ہے. سو یو وڈ ہیو اے اسٹینڈرڈ پروڈکٹ آف سم ایکسپریشن. اب اس کو کیسے امپلیمنٹ کریں گے, بیسکلی ہر جو میکس ٹرم ہے دیٹ وڈ بی امپلیمنٹڈ تھرو این اور گیٹ. So you would have a number of OR gates. Basically اگر آپ دیکھیں 8 max terms آپ کو فنکشن ٹیبل میں نظر آ رہی ہیں. So you would have 8 OR gates. Now the output of all those 8 OR gates would be connected to an AND gate, of course, which is doing what? It is doing the sum of products, or rather product of sums. The AND gate has 8 inputs, of course. So let us have a look at the 3 different circuits. اس کو دوبارہ بعد میں سمرائز کریں گے. The product of sum based implementation of the adjacent ones detector circuit is shown, implemented directly from the function table. This implementation uses maximum number of gates. The total gate count is 1 8 input AND gate, 8 4 input OR gates, and 10 NOT gates. Altogether 19 gates are required. Now the gates required in this product of sum implementation are equal to the gates required in the sum of product implementation. So the increased number of gates mean increased cost of the circuit, the size of the circuit of course increases, the power requirement increases, and the propagation delay is of the order of 3 gates. An appropriate way to implement the adjacent ones detector circuit is to simplify the product of sum Boolean expression represented by the function table, and then from the simplified Boolean expression the circuit can be implemented. The circuit of course would be simpler as compared to the standard product of sum based expression. The function table information is directly mapped to a 4 variable Karnaugh map. The zeros are grouped together forming 3 sum terms. The 3 terms are A plus C, B plus C, and B plus D. The simplified product of sum based circuit is implemented using 3 2-input OR gates and a single 3-input AND gate. The total circuit count is 4 gates. The cost of the circuit reduces, the size of the circuit reduces, the power requirement of the circuit reduces, and the propagation delay has reduced from 3-gate delay to 2-gate delay. The simplified 4-gate circuit can be implemented using only NOR gates without a change in the total number of gates. Bubbles representing NOT gates are placed at the output of the 3 OR gates, converting the 3 OR gates to NOR gates. To balance out the 3 NOT gates added at the outputs of the 3 OR gates, 3 bubbles representing 3 NOT gates are also placed at the 3 inputs of the AND gate. The resulting AND gate symbol with 3 bubbles at the 3 inputs is an alternate symbol for a 3-input NOR gate. the NOR based circuit is shown. We have seen three different implementations based on the product of sum expression. The original circuit was based directly on the standard product of sum expression. You have a function table, you have the max terms, you can just write out all the max terms, and you can then directly implement each max term using an OR gate. Basically max terms जो हैं वो क्या represent कर रहे हैं? Sum terms represent कर रहे हैं. Well, we have said that the appropriate way to implement a circuit is to first simplify the Boolean expression representing the function of the circuit and then implement it. The idea is to reduce the circuit size to reduce the number of gates. We also looked at alternate ways of implementing circuits. Basically, NAND gates को हमने देखा था. Using all NAND gates, you can implement a circuit. Using all NOR gates, you can implement a circuit. क्यों हम यूज कर रहे हैं? बेसिकली वी मेंशन दैट ए NAND गेट इज ए यूनिवर्सल गेट. सिमिलरली ए NOR गेट इज ए यूनिवर्सल गेट. सो इफ यू हैव ए NAND गेट और ए NOR गेट, you can in fact implement any gate. So by implementing the same circuit, the adjacent ones circuit using NAND gates and NOR gates, we have proved that actually you can represent any circuit using NAND and NOR gates. एक फायदा इसका ये भी है कि if you look at an IC integrated circuit, उसमें 4 NAND gates हैं. So basically, when you are implementing a circuit which requires, let's say, 4 NAND gates, you can only use a single chip. अगर वही circuit आप बना रहे हैं using an OR gate, AND gate, different gates, so different integrated circuits use होंगे. So again, the circuit size would increase. So it is better to implement a circuit using the same set of gates. Now we have talked about 2 different ways of implementing combinational circuits. How do we look at the performance of a combination circuit? जैसे हमने शुरू में बात की थी, आपको अगर याद हो, टाइमिंग डायग्राम की हमने बात की थी. टाइमिंग डायग्राम्स क्या रिप्रेजेंट करते हैं? इफ यू हैव अ सर्टेन सर्किट, यू अप्लाई सर्टेन इनपुट्स एंड दोज इनपुट्स आर चेंजिंग ओवर पीरियड ऑफ टाइम. So you need to check the output for that certain period of time. कैसे करेंगे? Through a timing diagram. So basically, when you implement the adjacent ones circuit या कोई और भी circuit, then you have to check its performance, its operation for a certain time period. ओके उस टाइम पीरियड में कौन से इनपुट सप्लाई करेंगे? बेसिकली आपने टेस्ट करना है कि वो जो फंक्शन टेबल आपने बनाया, जिसके तहत आपने फिर अल्टीमेटली सर्किट बनाया था, वही वाले इनपुट्स आप अप्लाई करेंगे और देखेंगे आउटपुट पे क्या वही चीज आ रही है कि नहीं. सो बेसिकली वी आर नाउ गोइंग टू हैव अ लुक एट द टाइमिंग डायग्राम एंड सी इफ आवर सर्किट actually gives the values which we are looking for. The timing diagram describes the operation of the circuit for the product of sum based simplified circuit for the intervals T0 to T8. A, B, C and D are the inputs to the circuit. The timing diagrams show the inputs A, B, C and D changing with time. The timing signals 1, 2 and 3 represent the outputs of the OR gates 1, 2 and 3. The timing signal F represents the output of the circuit. At interval T0, the input A, B, C, D to the circuit is 0, 0, 0, 0. The outputs of the 3 OR gates are 0, 0 and 0, and the circuit output is also 0. Now this can be seen in the timing diagram. For interval T0, the timing diagram 1, 2, 3 and F shows logic 0. At the interval T3, the input ABCD to the circuit is 0, 0, 1, 1. Now you have 2 adjacent ones, so the output of the circuit F should show a 1. Now let's have a look at the timing diagram. The outputs of OR gates 1, 2 and 3 are all ones, as can be seen in the timing diagram. The output F is also a 1. At interval T6, the input ABCD to the circuit is 0, 1, 1, 0. The outputs of OR gates 1, 2 and 3 are all ones. The output F is 1, indicating adjacent ones. The operation of the circuit, which is based on product of sums simplified expression, also proves that the product of sum based expression determined from the truth table and the Karnoff map results in a circuit which operates in an identical manner to that of a sum of product based circuit. We have just looked at the timing diagram of the adjacent ones detector circuit. As you saw, we can represent all the inputs and the output and the outputs of different gates within the circuit through a timing diagram. And then for different time intervals, we can in fact see the different outputs, the intermediate outputs and the inputs. And we can verify the operation of the circuit. The other thing which we saw in this particular diagram was that we used the product of sum implementation of the circuit, and we applied the different inputs, and we determined that the product of sum circuit does give you the appropriate output. So it is equivalent to a sum of product circuit. Now let's talk about active high levels and active low levels. What are active high and active low levels? Up till now, we have talked about different circuits. For example, this particular circuit detecting adjacent ones. Now, if the circuit detects adjacent ones, what is the output? Basically, the output is 1. Well, we could have said that if the circuit detects adjacent ones, the output should be 0. इसी तरह हमने पहले भी सर्किट्स स्टडी किए थे, जैसे कंपैरेटर सर्किट था. कंपैरेटर सर्किट में वी हैड 4 इनपुट्स रिप्रेजेंटिंग 2 बिट नंबर्स. तो वो जब कंपेयर होते थे तो हमारे पास 3 आउटपुट्स थी. तो अगर वो दोनों नंबर इक्वल हैं तो जो इक्वल वाली आउटपुट है उस पे 1 आ जाता था. क्या उस पे 0 आ सकता है? सो लेट अस सी. नाउ इफ यू लुक एट द कंपैरेटर सर्किट, उसके जो 3 आउटपुट्स हैं नॉर्मल स्टेट में क्या होते हैं? तीनों जो आउटपुट्स हैं वो 0 पे होते हैं. इफ ए इज इक्वल टू बी, तो वो जो इक्वल वाला आउटपुट है ए इक्वल्स टू बी, वो क्या होता है, उसकी स्टेट क्या होती है? इट गोज टू लॉजिक 1 और बाइनरी 1. सिमिलरली इफ ए इज ग्रेटर देन बी, नॉर्मल स्टेट में ए ग्रेटर टू बी जो आउटपुट है वो क्या होगा? 0 है. जब भी ए becomes greater than b, the output goes to 1. Similarly, the output a less than b, normal state में 0 होगा. जब भी number a is less than b, the output goes to 1. So basically, हम इस circuit के output को कहेंगे it is an active high, right? The output is active high or logic high. Now we could design this comparator circuit so that the outputs normal state में जो है outputs वो 1 हो. जब भी a इक्वल्स टू b हो आउटपुट 0 हो जाए. इसी तरह जब भी a इज ग्रेटर देन b आउटपुट 0 हो जाए. इसी तरह a जब भी लेस देन b हो आउटपुट 0 हो जाए. इस किस्म का अगर जब सर्किट होगा उसको कहेंगे उसकी जो आउटपुट है द आउटपुट स्टेट इज एक्टिव लो और लॉजिक लो. ओके, ये जो हमने कंपैरेटर सर्किट बनाया था इसकी स्टेट जो है आउटपुट स्टेट है आउटपुट हाई, एक्टिव हाई. इसको अगर एक्टिव लो बनाना है तो क्या करेंगे? बेसिकली हम आउटपुट्स पे इन्वर्टर्स लगा देंगे. इन्वर्टर्स को सिंबॉलिकली कैसे रिप्रेजेंट करते हैं? बाय बबल. सो बेसिकली अगर कंपैरेटर सर्किट के डायग्राम के आउटपुट पे अगर बबल्स लगा दें, इट वुड इंडिकेट एन एक्टिव लो आउटपुट. इसी तरह किसी भी सर्किट के इनपुट को भी एक्टिव लो बनाया जा सकता है. कंसिडरिंग द कंपैरेटर सर्किट, इसको जब हम 1 देते हैं, 1 is represented by of course binary 1. Now we could say that 1 is represented by logic 0. So अगर logic 0 दे रहे हैं, for the circuit to work it should invert it and take it as a 1. So क्या करेंगे? इनपुट पे भी हमें बबल लगाना पड़ेगा. So that means the comparator circuit is accepting an active low input or logic low input. Let us look at the adjacent ones circuit. नॉर्मल स्टेट में adjacent 1 का आउटपुट क्या है? इट इज 0. जब भी वो adjacent 1 डिटेक्ट करता है आउटपुट क्या हो जाता है? 1 हो जाता है. तो इसका जो आउटपुट है इट इज एक्टिव हाई. ठीक है. अगर इसको एक्टिव लो बनाना है दैट मीन्स नॉर्मल स्टेट में आउटपुट पे 1 दे रहा हो, जो ही वो 2 adjacent 1 डिटेक्ट करता है आउटपुट 0 हो जाना चाहिए. सो देन द सर्किट वुड बिकम, द आउटपुट वुड बिकम एक्टिव लो. एक्टिव लो आउटपुट बनाने के लिए क्या करना पड़ेगा? उसके आउटपुट पे इन्वर्टर लगाना पड़ेगा. इन्वर्टर को कैसे रिप्रेजेंट करते हैं? थ्रू ए बबल. सो डायग्राम में अगर एडजेसेंट 1 सर्किट के आउटपुट पे बबल नजर आ रहा है तो इसका मतलब है इट हैज एन एक्टिव लो आउटपुट. سملرلی ایڈجسٹنٹ 1 کا جو سرکٹ ہے اس کے ان پٹ کو ہم ایکٹیو لو بنا سکتے ہیں. اس میں جو ہم ایڈجسٹنٹ ونس ڈیٹیکٹ کر رہے ہیں, ونس کیسے بیسکلی ریپرزینٹ کرتے ہیں, بائی بائنری ونس. لیٹس سپوز اگر اس ایڈجسٹنٹ 1 سرکٹ کو ایکٹیو لو ان پٹ دیں تو کیا کرنا ہوگا, اس کے ان پٹ پہ ایک انورٹر لگانا ہوگا. سو اگر ڈائیگرام اس کا دیکھا جائے ایڈجسٹنٹ 1 سرکٹ کا, اس کے ان پٹ پہ ببلز آپ کو نظر آئیں گے. ببلز وڈ آف کورس انڈیکیٹ دیٹ the input is active low. Now let us consider the 4 gates which we talked about: the AND gate, the NAND gate, the OR gate and the NOR gate. اگر AND gate کے اگر سمبل کو آپ یاد ہو, اس کے دونوں ان پٹس جو ہیں وہ ایکٹیو ہائی ہیں, رائٹ. سو 1 and 1 آؤٹ پٹ کیا آ رہا ہے, اٹ از این ایکٹیو ہائی آؤٹ پٹ. 1 and 1 gives you 1 آؤٹ پٹ. NAND گیٹ کو اگر دیکھیں, NAND گیٹ کا سمبل جو اٹ از سملر ٹو دیٹ AND گیٹ سمبل ود اے ببل ایٹ دی آؤٹ پٹ. کیسے کام کرتا ہے, بیسکلی 1 and 1 ایکٹیو ہائیز ان پٹس, آؤٹ پٹ پہ کیا آ رہا ہے, 0 آ رہا ہے, ایکٹیو لو آؤٹ پٹ. اور گیٹ کو ذرا دیکھیں, اور گیٹ کے جو دونوں ان پٹ ہیں ادھر ببل نہیں ہے, دیٹ مینس 1 اور 1 دونوں ایکٹیو ہائی ان پٹس ہیں. آؤٹ پٹ پہ کیا آ رہا ہے, اگر دونوں میں سے کوئی بھی ایک 1 ہو, دی آؤٹ پٹ از اے 1, سو آؤٹ پٹ از ایکٹیو ہائی. نور گیٹ کو دیکھیں, نور گیٹ کا سمبل اٹس سملر ٹو اور گیٹ بٹ اٹ ہیز اے ببل ایٹ دی آؤٹ پٹ. سو وٹ ڈز دس مین, نور گیٹ کے ان پٹ پہ اگر 2 ایکٹیو ہائی دیں, 1 اور 1, دی آؤٹ پٹ از 0, ایکٹیو لو ہونا چاہیے. ٹھیک ہے. سو جسٹ ریمبر دس رول, کوئی بھی سرکٹ جو ہو وہ ایکٹیو ہائی ان پٹ ہو سکتا ہے, ایکٹیو ہائی آؤٹ پٹ ہو سکتا ہے, ایکٹیو لو ان پٹ ہو سکتا ہے, ایکٹیو لو آؤٹ پٹ ہو سکتا ہے, کمبینیشن بھی ہو سکتی ہے, ایکٹیو ہائی ان پٹ, ایکٹیو لو آؤٹ پٹ, اسی طرح ایکٹیو لو ان پٹ, ایکٹیو ہائی آؤٹ پٹ. سو ڈفرنٹ 4 کمبینیشن ہو سکتی ہیں اس میں. انفیکٹ ابھی جو ہم نے 2 ایڈجسٹنٹ سرکٹ بنایا اس کو ہم ایکٹیو لو بنا کے دیکھتے ہیں اس میں. تو لیٹ اس سی, let's have a diagram, اس کو ہم چیک کرتے ہیں through a timing diagram. Let us quickly have a look at the 4 gates. AND gate performs AND operation on 2 active high inputs to result in an active high output. Similarly, NAND gate performs AND operation on 2 active high inputs resulting in an active low output. OR gate performs OR operation on 2 active high inputs to result in an active high output. Similarly, NOR gate performs OR operation on 2 active high inputs to result in an active low output. The simplified sum of product based implementation has an active high output. The circuit can be implemented to have an active low output by connecting a NOT gate at the output of the circuit. Now, whenever adjacent ones are detected, the circuit output is set to 0. The circuit is also shown to have active high inputs. The circuit can work with active low inputs, producing an active high output if NOT gates are connected to the inputs of all the AND gates. Consider now the sum of product based circuit which has active high inputs and active high outputs. If the inputs of the circuit are made active low and the output of the circuit is also made active low, then bubbles are added at all inputs of the 3 AND gates. A bubble is also added to the output of the OR gate. The bubbles added at the input of the AND gate represent the alternate symbol for the NOR gate. Similarly, the bubble added to the output of the OR gate also makes it a NOR gate. By modifying the circuit to have active low inputs and outputs, the circuit sets the output F to active 0 to indicate detection of adjacent ones. Since the inputs are also represented by active low, therefore the input ABCD equals to 0, 0, 0, 0 actually represents 1, 1, 1, 1. Similarly, ABCD, active low input 0, 0, 0, 1 actually represents 1, 1, 1, 0. Let us now have a look at the timing diagram. The timing diagram describes the operation of the circuit for the intervals T0 to T8. The timing signals A, B, C, and D represent the active low inputs applied at the inputs of the circuit. The timing signals 1, 2, and 3 represent the outputs of the NOR gates 1, 2, and 3 respectively. The timing signal F represents the active low output. At interval T0, the active low input at inputs A, B, C, D is 0, 0, 0, 0, which actually represents 1, 1, 1, 1. The active low output F is 0, which indicates that adjacent ones have been detected. Similarly, at intervals T1 to T4, the active low inputs A, B, C, D are 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 0, which actually represents the numbers 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, and 1, 0, 1, 1. The output is 0, indicating that adjacent ones have been detected. Up till now, we have been assuming that logic circuits work with an active logic level of 1. جب بھی وہ ایکٹیویٹ ہوں گے تو logic level 1 ہونا چاہیے. ضروری نہیں ہے. As we have seen in the example, logic circuits can operate with active levels as zeros and ones. So in the course we will see different circuits جو 0 پہ بھی ایکٹیویٹ ہو رہے ہیں اور 1 پہ بھی ایکٹیویٹ ہو رہے ہیں. different examples دیکھیں گے. Now let us look at another example, the example of a odd parity generator. ہم سرکٹ بنائیں گے جو کہ آڈ پیریٹی جنریٹ کرے گا. Now, if you remember, we mentioned that when we transmit data from one end to the other end, اس میں کچھ بٹس جو ہیں وہ خراب ہو سکتے ہیں ڈیو ٹو سم ایکسٹرنل نوائز. 0 سے 1 ہو جائے گا, 1 سے 0 ہو جائے گا. So by adding a parity bit, we can detect a single bit error. اوکے ہوگا کیا, وی ہیو لیٹس سے 4 بٹ ڈیٹا, وہ ہم نے ایک اینڈ سے دوسرے اینڈ پہ بھیجنا ہے. ہم کیا کریں گے, ساتھ میں ایک پیریٹی بٹ جو ہوگی, دیٹ مینس 5 بٹ ڈیٹا ہم بھیجیں گے دوسرے اینڈ پہ. نا اگر ہم آڈ پیریٹی یوز کر رہے ہیں, دیٹ مینس جو 4 بٹ ڈیٹا ہے اس میں ہم نمبر آف ونس کاؤنٹ کریں گے. اگر وہ 0 ہے, ٹوٹل نمبر آف ونس از 0, دین دی پیریٹی شوڈ بی سیٹ ٹو 1. تو جو 5 بٹ جائے گا اس میں پیریٹی 1 ہوگی. اگر جو 4 بٹ ڈیٹا ہے اس میں جو نمبر آف ونز ہیں وہ آڈ نمبر ہے, 1 ہے یا 3 ہے, دین دی پیریٹی بٹ وڈ بی سیٹ ٹو 0. سو دی ٹوٹل نمبر آف ونز ان دی 5 بٹ ڈیٹا ریمینس این آڈ نمبر. ناؤ سرکٹ جو ہے آڈ بٹ پیریٹی جنریٹر کا کیسے بنائے گا, ویل لیٹ اس جسٹ ڈسکس دیٹ. بیسکلی ہم نے ایک فنکشن ٹیبل بنانا ہے, فنکشن ڈائیگرام بنانا ہے, which would indicate the input standard assumption. Okay, let's function diagram of the odd parity generator circuit. Now let us use 4-bit data set. So کتنے inputs ہوں گے, کتنے tables ہوں گے, basically کیونکہ function table میں 16 different inputs ہیں. That means وہ جو 4 bit data ہے 16 different combinations میں ہیں. Now output کیا, output will be packed with. So for example, the data is 0, 0, 0, 0. چاروں bits 0 ہیں. So parity bit کیا ہونی چاہیے, کیونکہ odd parity bit ہم یوز کر رہے ہیں تو odd parity bit کی ویلیو 1 ہونی چاہیے. So output would be 1 for the input combination 0, 0, 0, 0. Similarly, اگر آپ کے input combination 0, 0, 0, 1 ہے تو output parity bit کیا ہونی چاہیے, basically to keep the number of ones equal to odd, the parity bit should be 0. So similarly, آپ یہ جو 16 combinations ہیں ان کی آپ parity bit determine کر سکتے ہیں. So اس طرح آپ کا function table complete ہو جائے گا. جیسے ہم نے پہلے ایگزامپل ایڈجسنٹ ونس کے کیس میں کیا تھا, آپ 2 قسم کی ایکسپریشن ادھر سے بنا سکتے ہیں, 2 قسم کے سرکٹس بنا سکتے ہیں اس میں. سو لیٹ اس اسیوم کہ اس کیس میں ہم سم آف پروڈکٹ ایکسپریشن کو یوز کرتے ہیں اور اسی کو ہم امپلیمنٹ کرتے ہیں ان دی فارم آف اے سرکٹ. سو سم آف پروڈکٹ ایکسپریشن کیا ہوگی, جتنے بھی مین ٹرمز آ رہے ہیں اس فنکشن میں ان کو اگر آپ لکھ لیں ایکسپریشن کی فارم میں اور ان کو آپ امپلیمنٹ کر لیں یوزنگ وچ گیٹس, سم آف پروڈکٹ ایکسپریشن ہے ویل اینڈ گیٹس ہوں گے. سو جتنے بھی پروڈکٹ ٹرمز ہیں, مین ٹرمز ہیں, ان کو آپ امپلیمنٹ کریں گے یوزنگ اینڈ گیٹس. ان سارے اینڈ گیٹس کا جو آؤٹ پٹ ہے وہ کس کو کنیکٹ ہوگا, ایک اور گیٹ کو. اوکے, سو بیسکلی یہ آپ کا سرکٹ بن جائے گا اس میں. Now this, as I said, would use a large number of gates. اس کو اگر ہم نے ریڈیوس کرنا ہے, کیا کرنا ہوگا, سمپلیفائی کر لیں اس میں. We would look at the detailed implementation of the odd parity generator circuit in the next lecture. Function diagram بنائیں گے, expression لکھیں گے اور combination circuit بنائیں گے. Till the next lecture, خدا حافظ and السلام علیکم.